Hello, Algebra 2. So here we go. This is going to be a little bit intense today, but that's okay because then Monday is nothing but review to kind of let the concepts simmer in your brain. So the first thing we're going to do is just look at properties of exponents. So hopefully you remember some things, starting off with any number raised to the 0 power is going to be 1. And we talked about in class why that is, the pattern that it follows, but that would make the video longer right now, so I'm not going to do that. Then we have our negative exponents. So whenever you see a negative on an exponent, remember it has nothing to do with the positive negative of a value. It just is like an action button. So if you see it in the denominator, it means move the value to the numerator. Okay, if you see it in the numerator, it means move whatever the value was to the denominator. So it's like an action button, and once you take that action, you remove the negative. All right, then we get to the product rule. When you multiply the same base, you're just adding the exponent, because remember, 2 squared times 2 cubed would equal 2 times 2, and then 2 times 2 times 2. So you'd have 5 2's there. So you're adding your exponents. That would be 2 to the 5th. So y to the 4th times y to the 7th, y to the 11th. When we divide, you're subtracting. What you're really doing, though, is canceling out. So let's go ahead. So this is showing the subtraction. In this example, you would have x to the 5 minus 2, which gives you x cubed. However, if your number on the bottom is bigger, so for instance, if I had x squared over x to the 5, I would then, rather than doing the subtraction and having to deal with a negative exponent, I would just take 2 of these, would cancel with 2 of those, so you would have 1 over x cubed. All right, this is harder to do in a video than it is up in front, but the idea is you could just do your subtraction, and when you get a negative exponent, adjust, or always taking away the smaller from the larger, leave your answer where the larger term was sitting. Okay. Over here, we know the distributive property. It means to multiply. Since there's no addition or subtraction, you're just multiplying the 2 powers together. So here we have x to the 5th raised to the 4th, so 5 times 4 is 20. Now, if you have several values inside the parentheses, because there's no addition or subtraction, you can distribute to both terms. So for instance, down here, that 2 will distribute to everybody. So I'll have 3 squared times x squared times y squared, which can simplify out to 9x squared y squared. Oh, I forgot to do the distribution on our quotient. So even if it's a quotient, you can still distribute and get a to the m over b to the n. I guess they're both to the n. So down here we see this would be x to the 4th over y to the 4th. Now, properties of the radicals. If 2 terms share the same radical, you can work in both ways. If they are in their own separate radical, you can join them under one radical, or if it's 2 terms under one radical, you can split them up so they each have their own. So in this example down here, these are both cubed roots, so I can join 4 times 2, which is 8, and then using our little half sheet, we know the cubed root of 8 is 2, where you couldn't see how to simplify that when they were under their own radical. Same thing is true if it is a quotient. Sometimes it's helpful to break it up, each one to its own, or so you can want to recognize this in both directions. Sometimes it's helpful just to put it all under one radical. So for instance here, we have the 4th root of 162 over 2, which is the 4th root of 81, And the fourth root of 81, if you look at your chart, is going to be 3. All right, so those are the properties of exponents. This is going to play a big role in chapter 6 when we do logs as well. So you want to get really comfortable with these. But let's do some examples. So this first one, notice we are multiplying the same base. So that would be using our product rule, we're going to add the exponents. So 2 to the 3/4 plus 1/2. That means we need a common denominator. So this will be 2 to the 3/4 plus 2/4. And that would give us 2 to the 5/4. And you can just leave it as an improper fraction. That's fine. We're just utilizing the properties here. The next one, we have 3 to the 1 over 3 to the 1/4. So if I'm dividing the same base, I can subtract. So this will be 3, 1 minus 1/4, which gives us 3 to the 3/4, because you can write 1 as 4/4. Now we start to get a little more complicated. Notice that my 20 and my 5 have the same exponent. So sometimes it's nice to just focus on the numbers. Since they have the same exponent, I can factor it out. So this becomes 20 over 5 raised to the 3/2. And so now I can simplify 20 over 5 is 4. And we get 4 raised to the 3/2. Remember, you always want to do the denominator first because that's a root. So the square root of 4, what I'm really doing here is 4 to the 1/2 cubed. So this is going to give me 2 cubed, and we know that equals 8. On the next one, there's nothing really to simplify inside. It's not the same base. They're not the same exponents. You really only have one option, and that is to distribute. So that gives me 5 to the 3/3 times 7 to the 3/4. And that really can only be simplified since 3/3 is 1 times 7 to the 3/4. And just as a review question, remember how to write this as a radical notation. So 5 stays as 5. 7 to the 3/4 is also the 4th root of 7 cubed. So don't forget, you can write things either way. Okay, now it's going to get a little more interesting. We have to simplify higher roots than just square roots. You know how to simplify things like the square root of 24 or the square root of 18, where you pull out the perfect squares. Well, now you're doing it with the cube, so you want to have your little half sheet handy, and you're looking under the column that is cubes, and you're trying to find something that is a factor of 135, but a perfect cube. So it turns out that 27 times 5 would give me 135. So then we look at, well, how can I rewrite 27? That is 3 cubed, and 5 just stays here as the cubed root of 5, because remember, I can give each one its own radical. And as soon as your power and your root are the same, these will cancel, so this simplifies to 3 times the cubed root of 5. So you want to be able to use that little half sheet to find your factors. Because the idea is you're not going to be using a calculator. So you want to be able to do these, you want to be able to break things down rather than making them bigger. So here we have the cubed root of 12 times the cubed root of 18. I don't want to sit here and multiply 12 times 18 because I'm just going to have to break it down again. So we're going to kind of look at what are some of the common factors of 12 and 18. Well, I know that 12 is 6 times 2. 18 is 6 times 3. And notice what happened is I really have here 6, a 6, and another product of 6. So I have 6 cubed. As soon as my power and root are the same, they cancel, and that simplifies out to 6. So we didn't have to multiply 12 times 18, which would have given us 216, and then you could take it, but again, you're not going to have a calculator. So now we're going to look at operating, what kind of, when you're adding and subtracting, you want to have like terms. In this case, that means you want to have like radicals. So everything that is in the radical needs to be the same. So down here I have the fourth root of 10 and the fourth root of 10. I have one of these and 7 of these. They are like terms, so I have 8 fourth root of 10. So it's kind of like adding 1x plus 7x. The radical just kind of carries along. You're just adding the coefficient. And it doesn't matter whether it comes in radical form or rational exponent form. Here I have the same term, 8 to the 1/5. So I just add 2 plus 10. So I have 12 times 8 to the 1/5. And that would be your answer. Now what happens when you don't have the same? So that means we have to create the same radical. But you have a little bit of a gift here because this cubed root of 2 cannot be simplified. That means I want to be able to write 54 as something times 2 because I want there to be a cubed root of 2. So 54 divided by 2 is 27. So I can rewrite this. This is the cubed root. 27 is 3 cubed times the cubed root of 2. And that simplifies out to 3 cubed root of 2 minus the cubed root of 2. So now we're bringing in our other term, and we just do the coefficients. 3 minus 1 is 2. That's how many cubed root of 2's I have. So use the fact that sometimes you are given a clue which tells you what you want for that common radical. Okay, so it's going to get a little more difficult on this side. Remember, you're not allowed to have a radical or a rational exponent in the denominator. So before we would rationalize by multiplying top and bottom by what that radical was that was in the denominator. Now that we have a higher power for our radicals, for our roots, it's going to affect how we rationalize the denominator. So we always want to make sure, well, let me kind of relate this to something. If I had given you 3 over the square root of 5, remember there's a 2 there. The reason why we multiplied by rad 5 over rad 5, because those became 5 squared. It gave us 2 of them. Remember, when your root and your power are the same, they cancel each other out. Well, what's going to happen now is we're going to have higher powers or higher roots that we have to accommodate. So over here, I'm going to leave my numerator the same. I have the 5th root of 7. On the bottom, I do have the 5th root of 8, but I would need 4 more 8s for this to work out, which is a really huge number. So what we're going to do is, can I break 8 down into a power of something? So remember, 8 is the same thing as 2 cubed. That helps a lot because what I have now is I have at least 3 of the powers that I need. I need to have a total of 5 so I can cancel my radical. So I'm going to multiply the top by the 5th root of 2 squared over the 5th root of 2 squared. The reason why we do that is now I can utilize my property of exponents that says I add the exponents when I'm multiplying the base. So this is the 5th root of 2 to the 5th. That is going to let me cancel my radical. So in my final answer, I'm just going to have a 2 on the bottom, and on top I have the same root. So I have a 7 and I have a 4. So that's the 5th root of 28, and that would be your final answer. Okay, so your goal is to get the power and the root to be the same so that you can cancel it out. And And if possible, make that initial number smaller so that you can raise it to a power without going off of, the fourth power of 8 is what I would have had to do if I didn't break that down into 2 cubed. However, do not always just immediately start doing that, because sometimes, remember, if I have the same root on top and bottom, you don't always want to just go at one strategy. So here I could actually simplify this. 4th root of 80 over 5 is the same thing as the 4th root then of 16, which is 2. All right, so sometimes you can just simplify it and the numbers will cancel out the denominator. Other times you are going to have to rationalize that denominator. So it's always good to try and simplify first as a general rule. Okay, there is no day 2 because we are on block scheduling now. So let's finish this off. When you have a really long problem, like this one, number A, I strongly suggest you take it step by step and break it up into each individual problem. So I have the 5th root of 4. I have, which I can't do anything with, I have the 5th root of a to the 8th. What I'm going to do with that is I'm going to write that as a to the 5th times a cubed, because remember you add exponents, so I can break it up as 2 different bases. 5 plus 3 is 8. I'm going to break up b to the 14th in such a way that I have a multiple of 5, the biggest multiple of 5 that goes into 14. So I'm going to break this up as b to the 10th times b to the 4th, because 10 plus 4 is 14. And then c to the 5th is going to stay as it is. And then we're going to simplify this term by term. So this one, nothing. There's nothing you can do with that. It just is what it is, even if I made it 2 squared. This one, the a to the 5th, that a will come out, and this other one is going to stay underneath, because you always want anything left under a radical should have a smaller power than the root. Otherwise, you could have still pulled something out. Now, b to the 10th, if you remember, we can write this as a fractional exponent. That's a power of 10 divided by 5, so you're really doing division with these. 10 divided by 5 is 2. So this will come out as b squared, and then the 5th root of b to the 4th stays there, and then c will come out because it has the equal power as the root. Putting it all together, what we have here is, let's pull out everyone that's outside of a radical. We have a, b squared, and c. And then everyone who is still under the 5th root gets put back together. So I have 4a cubed b to the 4th. And that would be your final answer. Of course, you're not winning $10 million doing these either, but yes, that would be your final answer. Okay, so here we have one of those problems that has a radical in the denominator. And so we want to make that radical go away. There's 2 ways to do this. I always do the harder way first, but this time, because it's the video, I'm going to go straight to the shortcut. 3 does not go evenly into 8. And I want 3 to evenly go into whatever is under that radical so that I can make the radical go away. So what I am going to do is, rather breaking this up, I know that 3 goes into 9. 9 is just 1 power greater than 8. So I'm going to multiply top and bottom by y, the cubed root of y. So really I'm multiplying by 1, so I'm not changing the problem. But this becomes then the cubed root of y to the 9th. Remember, if you wrote this as a rational, that's y to the 9th divided by 3. So my denominator, is going to be y cubed, and my numerator is going to be x times the cubed root of y. So sometimes it's actually easier to make the problem a little bit bigger, so long as you can just eliminate that denominator. All right. we have another problem here that's got several terms to it. So what I recommend with these is break it up so that we have 14 over 2 x over x to the 3/4 times y to the 1/3 over nothing, over 1 I guess, and 1 over z to the -6. So we're going to simplify it term by term. So 14 over 2, that's going to become 7. X over x to the 3/4, remember this is 1. So when you're dividing, you subtract exponents, so that becomes x to the 1/4. Y is fine as it is because it's in the numerator. You're not allowed to have a negative exponent in a simplified answer, so z to the 6 goes upstairs, and that is your final answer. Okay. Coming back over, we have the cubed root of 64 times y to the 6. So this is the cubed root of 4 cubed times the cubed root of y to the 6. This will come out as 4. Now, y cubed root of y to the 6, this is really 6 over 3. That comes out as y squared. Sometimes it's really helpful to write it as a rational exponent because then you can see how it simplifies. Now, here's the Eeyore problem. I call these Eeyore problems because anytime you go from an even root to an odd power with a variable, you are going to have to put that variable into absolute value signs. Why? Because we know that the square root of, or let's say the cubed root of -8, we know that's a -2. So odd roots, no problem. But if I take the square root of a -8, we know that has no solution, no real solution. So what happens if I have a variable? We know that what should come out should be positive when it's an even root. So when I have x squared, we know these cancel and I get x. But x is a variable. How do I know if that's a positive number or a negative number? The way you make sure it's a positive number is you throw absolute value signs around it. So we went from an even root to an odd power. So anytime you go even root to odd power, you're going to put absolute values. And again, this only applies to variables. So let's look at this problem here. We have x to the 4th and y to the 8th, and we're taking the 4th root of both. So on top, x to the 4th will come out as x, y will come out as y squared. Since I started with an even root and went to an odd power in the numerator, that goes under absolute values. Y squared is okay because that's anything squared is still going to be positive. All right. It's a minute detail, and we're not going to emphasize it too much. You might see one problem with that, okay? Okay, now we get down to rationalizing the denominator when you have more than one term. So we have already talked about this concept of conjugates when we did the radical roots and the imaginary roots, that they always came in conjugate pairs. Well, conjugates also are used in simplifying or rationalizing a denominator. So the conjugate of 5 plus root 3 is 5 minus root 3. So we multiply top and bottom by 5 minus root 3. On top, that's no problem. That's just going to be 5 minus root 3. On the bottom, remember, this is a plus b times a minus b. And when you multiply that, it gives you your difference of squares. So we can utilize that shortcut. This will become 5 times 5 minus root 3 times root 3. That's going to give us on top 5 minus rad 3, and on bottom 22. And we're done. Okay, so let's try this next one. If you want to pause and try it on your own, that's fine. We have 3 over rad 2 minus rad 7. So the conjugate will be rad 2 plus rad 7 over rad 2. So again, we're multiplying by 1, so we're not changing the fraction. So in the numerator, I just distribute the 3. That's not that big a deal. And on the denominator, I do my difference of squares. So rad 2 times rad 2 is 2, minus rad 7 times rad 7, and just then simplifying it, we have 3 rad 2 plus 3 rad 7 on top, all over negative 5. Okay? Almost there, guys. I know, this is intense. All right. So now again, adding and subtracting and trying to create like radicals. Notice this first term, I have the cubed root of 9 squared, and actually this is also the cubed root of 9 squared. One is written in radical form, one in rational exponential form, but they're both equivalent. So all I have to do is add the 4 and the 8, and then times the cubed root of 9 squared. Or, if you prefer, because I really don't care which form you write it in, you can also write it in this form. Okay? Last problem. All right. We do not have like radicals, but we want like radicals. So both of these can be simplified because notice here I have a power that is higher than my root. That means I can pull things out. So let's simplify this one first. 12, can't do anything with 12. I have the cubed root of 2, can't do anything with that. However, the cubed root of z to the 5th, I can write that as z cubed times z squared. So this will simplify to 12. A z will come out because that cubed will cancel with the radical. And then the 2 cubed roots get put back together. So I have 2 times z cubed. All right, that is simplified as much as I can, which kind of tells me that this is the radical I want to appear on the other side of my subtraction sign. So I have minus. So far we just have z. We have the cubed root of 54. Remember, 54 is 27 times 2. There's also this clue here that we expect there to be a cubed root of 2 in there somewhere. And then we also still have the cubed root of z squared. So here's going to be that common root. And the cubed root of 27, because remember this is the cubed root of 3 cubed, that'll come out as 3. So I have minus 3z. That came from here. And then I still have the cubed root of 2z squared. And that came from here. So I do have like radicals, which is what I was looking for, so we just combine our coefficients. 12z minus 3z, I believe is 9z, times the cubed root of 2z squared. These really take practice so that you get comfortable manipulating and using all those properties. So I know the classwork is going to be kind of intense. Just take one problem at a time and check your answers as you go.